Thanks for giving me this chance to share our research, recent research about this interesting topic between the machine learning and optimization, especially for combinatorial optimization, which we know is very challenging, right? So first, this is our team working on this interesting topic, including many PhD students who some of them have graduated and some of them have went to MIT for postdocs. And also they have some students in master degree and also got a job in many companies. But we try to have the joint goal to push the frontier of this exciting topic. So first, let's revisit some classic solvers. We call it solvers, like the IBM CPLEX, or Mosaic, or Groovy. They are very famous in solving different industry level optimization problems, especially for those like the mixture integer programming and also combinatorial optimization. And the basic idea is try to unify different kinds of the problems, like the routing problems, the coloring problems, or the maximum flow into a unified form, like the mixture integer programming, and they can be solved in a unified manner. And we have seen many professors and faculties try to start up their companies from the universities, because this is a relatively clean mathematical problem, right? As long as your solver is strong enough, is fast enough, maybe you can make money. And now we are in the era of AI, and we try to move out of this comfortable zone, because in very classic problems, the size of the problem, they are also deterministic. But in reality, in our many new applications, the problem size could be very massive, large, and we have in a dynamic environment, and many uncertainties do exist. So shall we introduce some idea of the AI, especially like machine learning, to address these challenges? For example, can we utilize the native AI computing resources like the NPU or GPU to accelerate the optimization? And the other idea is like the AlphaGo. Can we use some like reinforcement learning to learn the policy of solving the problem instead of using the expertise or some human experience? So this is a big picture. And if we think more about this, can we using two dimensions? The one is about the variables we want to solve. They can be both in the continuous space or in the discrete domain, right? And the other dimension is about the constraints, like the deep neural networks, like the convolutional neural networks. Usually we think they are unconstrained optimization, right? We just to compute the gradients and got the parameters. But in many real-world applications, we need to face the constrained problems, especially for those discrete constraints, making the problem much harder. So in this sense, we saw the many research, like the deep neural networks, could fall into this part, because we just trivially using gradient descent to update the parameters of the models. But like many graph problems, they could be in the discrete space, and they have many constraints, especially those non-trivial constraints, right? And we also witnessed the trend for this pipeline in terms of using machine learning, not only to solve the perception problems like image classification, but also decision problems. Just here, like the combinatorial optimization. And like the Yushu Banjo, he once wrote a first author paper, like a survey and a perspective paper in EJOR, European Journal of Operation Research, to talk about this interesting trend. And also like the CVPR 22 best paper, the name is about machine learning for solving minimum problems. It's also about machine learning for optimization. And like the American NSF, they have an initiative in 2021 about millions of dollars, $10 million $20 million about this topic, and they set up a team, including the members from the Georgia Tech, ISYE for optimization guys, and also like the CMU, Princeton for machine learning guys working together. So we can to make it more concrete. So think about many deep learning, which will solve the problems like the image classification or object detection. So usually we are using, like we said, in a continuous space to update the parameters, and there is no constraint. So we finally converge into like the transformer-like structure of the neural networks to solve the problems. But for decision making, like the graphs, we have constraints, we have discrete structures. So the neural network architecture could be more diverse and still in the open space. For example, we have a network called Pointer Network, which was devised by Google DeepMind 10 years ago. So the purpose of this network could to make sure the output could always satisfy the certain constraints. But the challenge is how can you invent such kind of architectures to enforce the hard constraints in your problems. That could be case by case. There is no unified paradigm could solve all kinds of different constraints. So this is the facts. So today I will talk about 3 aspects of our research. The first is about AI aided. That means we stand on the shoulder of a giant. So we know we have many classic strong solvers and algorithms. So can we combine AI with these great tools to make the solver more efficient or more scalable or do more available? The second topic is about AI native. So we just forget about these classic solvers. Can we use some more neural networks, pipelines to directly solve the problems? And the third part is about application. So usually about design, like the EDA, electric design of automation, right? For placement and the routing or logic synthesis. The other one is about like the AI for drug. And also we may talk about something about quantum. Quantum circuits, design the quantum circuits. So the first part is about can we combine machine learning with traditional algorithms for graph problem solving? So the basic idea is that, so the most universal form of optimization is about the mixture linear programming, which is very standard form in many commercial solvers. So this is an example. So by giving these equations or non-equations, it's not friendly for machine learning models to solve them directly. So we observe that maybe we can transform these formulas into a bipartite graph. So in this bipartite graph, these nodes, in blue is about the variables, and this red node is about the formulas, and this edge is about the weights of all the coefficients of the formulas. And we also can give some labels in terms of the value in the right side of the equation, and also the constraint types, and assign them as the attributes of the nodes. So we can establish such kind of a graph, and they can be equally transformed into these formulas. Then, so we have a graph. We know it's more friendly and familiar to our models like graph neural networks, right? So then we can introduce graph neural networks to solve these problems in terms of like the either using supervised learning if you have the high quality solution of the given the formulas, or you even using some self-supervised learning or unsupervised learning, because we can always like reinforcement learning, we can always try to get a solution and you can update the models. And we also, of course, do something about how to improve the backbone of the the GN, right? We have many variants of the graph neural networks in terms of how to enhance its scalability or enhance its expressiveness. And we do have some works in these areas, but due to time limitation, I will quickly go through this part. And another important thing is about the so-called equivariance. So we have, so the problem or the graph has some geometric properties like the permutation invariance or some rotation invariance. For example, the TSP, travel salesman problem, right? We call it, it has some invariance about like the scale, right? Is invariant, and also the node permutation is invariant. So how can we incorporate this invariance or symmetries into the backbones or into the models is important to improve the generalization ability of the models. So there are many new challenges. So we also have some deep dive into the graph transformers or seeking for more efficient architecture of the graph neural networks. And we have some papers in recently in Europe and ICR or ICML. And it is worth to mention that we have the Europe's paper last year. It's called SG former. This is the first one we can make it scale on the billion level number of nodes on our commodity GPU. It's about a graph transformer. It's not only a GN, right? We know the GN is in linear complexity of the nodes, but the transformer, graph transformer, by default is n square, but we try to linearize the complexity to make it more scalable on on large graphs. And another very, I think, practical way to improve the solver is about, we call it a presolve. There are many, like the mixed integer programming problem, here is the raw form. And we can find some presolve, we call it presolver. We have a pool of the presolvers, 1, 2, 3, 2K. And once we can apply a series of these presolvers, then the new problem instance could be simplified. It will be much simpler to solve than the original form. So the ways how can we choose and set the hyperparameters of these presolvers to make the problem easy to solve. And in the commercial solvers like the Groovy, we know it's a black box, and even most cases, most cases, it's by default. So they just recommend you a default setting of these presolvers. But to us, we try to using machine learning, like reinforcement learning, to adaptively to select these candidates. If, for example, we only can select 3 to 5 presolves from these dozens of the candidates, and we can significantly speed up the problem solving because we can find a better simplified form to then this part is given to the classical solver, but we will enhance this part by very personalized presolving. So this is also our ICOR 2024 paper. And also we can do something about instance augmentation in images, and the data augmentation could be very trivial, right? We just to do rotating and swapping, enlarging, right? But for these kind of nonlinear and complicated problem instances, the data augmentation could be especially non-trivial. So can we introduce machine learning to augment the problem instances? Because in many industrial applications, these instances are very few. We only have a very small number of the instances. So it's hard to train a model or to do hyperparameter optimization. So the basic idea, the problem is, can we develop a data augmentation methodology for mixed integer programming? This is an open question and have never been done before. So this is one of the first trials to develop this case. And this paper was a ICML spotlight in this year. And also, this is also the case for the satisfiability problem, which is also very classic and the important ones, like in the EDA and in the cryptos. People will always solve the set problems. And also we try to, this is the first, to our best knowledge, the first AI-aided one to perform data augmentation for set problems. As I just said, it is much more difficult and non-trivial than just images, because image is very intuitive, right? And you know that image, you rotate the image is still the same one. And even you do some cropping, right? The same. But for this nonlinear problems, it will be much more difficult because we want to maintain the distribution of the raw data, but we still need to maintain the difficulty of the instance. So it's non-trivial. So we made it in the last year's SIG-KDD. These are the technical details. I just omit this part. And we also have an improvement one in this year's ICOR. It's more adaptive and less knowledge-driven. And we also try to develop some universal or general purpose pre-processing techniques for problem solving. For example, we have many problems on the graph to solving, right? And the idea is, can we adaptively to modify the input graphs? Then the modified problem could be much easier to solve, but we still have the chance to find its optimal solution for the raw problems. So we introduced reinforcement learning on the like graph edit distance problem, the DAG scheduling, and like the Hamilton cycle problem. And we find our reinforcement learning based approach was very successful. And this is a joint work with the Alibaba Research Lab in Seattle. And the paper was published in NeurIPS 2021. We also have many applications, like we even with some collaboration with some the corporates in terms of the optimization scheduling of the elevators. And this is an online and dynamic problem. You need to not only to make decisions, but also try to do forecasting, because the elevators in a high building, we have maybe 8 or more elevators, and you need to predict the traffic flow, the people flow, right? And you make the decision. So this is the so-called predict and optimization problem. So we try to combine them together. This is our just the recent work in terms of these areas. Mostly were published in NeurIPS, ICML, and ICR. And the second part is about, can we develop a more native, AI native algorithm to solve the graph problems? And we try to list some popular constraints here. And some of the constraints, fortunately, we can find some neural architectures to make an end-to-end and trainable neural networks. So we can solve the very hard combinatorial problems like we do for image classification. We just have a forward inference, and it's highly efficient. For example, we can, sorry, there are some Chinese. We can speed up, compared with the commercial solver Groovy, about 400 times speed up compared with the Groovy, because it was running on the CPU, but our algorithm is a neural networks, so naturally it can run on a GPU. And we also try to give some theoretical studies about its error bound or violation bound in terms of the constraints. Some works was also published in like ICLEA 2023 and the CVPR 2022. So these are some technical details I will omit, but usually we could try to extract the raw features, and we introduce graph neural networks, and we also introduce some special architecture of the layer, some special layers like the single horn layer. So try to ensure the output would be a permutation matrix, so we can get a feasible solution. And also we try to extend our ideas into the quantum world. This is a classic neural networks, and we also try to think about could we invent a circuit, quantum circuit to do the similar things. But the behind the belief is that maybe quantum is a very amazing tool to solve the NP hard problem, right? But now we only turn to GPU and the CPU. So can we think about we have a very efficient QPU, and machine learning could be useful in extend its ability in terms of solving different kinds of the problems, right? So the basic fact is that actually the quantum circuit is also a kind of neural networks, and we can have the parameters on these circuits, and these parameters could be updated, so it can akin to the parameters of the neural networks. So finally, we managed to develop and invent this kind of the circuit, and we have many quantum components, and it's like we can do forward inference, and even we can do backward gradient-based update. So this architecture also is called the variational quantum algorithm. It's also a popular architecture. So it's actually a mixture, quantum and the classic computing mixture the architecture. So outside classic optimizer is responsible for updating the parameters of the circuits, and the circuits is used to obtain the solutions. So this paper was also published in ICML 2023, and we also have some works in terms of trying to train the latent space in a continuous space instead of the low high dimensional discrete space, and it's like the diffusion network. So we have so this paper was published in Europe 2023, and in that time we got maybe the best performance in terms of machine learning for optimization. So there are two problems. One is about TSP, one is about the max cut. And the basic idea is that we try to, like the diffusion, we try to train latent space offline in training stage. And then in the testing stage online, we introduce some techniques to do to enable gradient-based search for the solution. So in that sense, we can help improve the generalization ability of the solver, because in this very difficult and nonlinear problems, generalization ability is very important. So we not only rely on the training, we also try to improve the flexibility in testing. That means we have, under the diffusion network framework, we could do gradient-based search in the test time. So this could significantly improve the generalization ability of the model, and also the cost is not very high because we managed to do it in a gradient-based way, rather than just using some very brute force search. We also established some platform for evaluating the performance of the solvers. Even like the adversarial learning, right? We can simply to design or to manipulate some very bad cases to make the solver fail. So this idea could also be applied in combinatorial machine learning. This work was also in ICLR 2023. And we also try to do some open source. And we have a GitHub. It's about now got more than 1,000 stars in terms of our GitHub code repository. And we also try to support different kinds of the deep learning architectures, especially for those domestic ones in China, like the Jitter, Mandelsport, and Paddle. They are all Chinese domestic architectures. And we also have papers in the last 3 years in these areas. The last part is about application. So one is about, maybe you remember in 2021, Google have a Nature paper on they claim using reinforcement learning to design their TPU, right? But it's also very controversial. And in the same year, we just have a NeurIPS paper, also do a similar thing, but we open source it, and we also use the public data set, and we also make it more end-to-end. And in later, we still publish 2 papers in Europe. To this one, introduce GAN, or generative networks. So we're not only using the reinforcement learning to find the routines, we're even using a generative model to directly generate the routines. So this idea has also widely been adopted in recent research in search, right? Generative search. And the third one is about a more carefully designed approach to improve the performance significantly. And some of these works were adopted by many Chinese companies. And we also got some very positive feedbacks from like the Wolfgang Ecker, who is the German Academy of Science and Engineering and also a chair professor of TUM. So they said our work, DPR, was about 4 times faster than replace by their evaluation. And the replace was actually a representative work by DARPA, sponsored by DARPA on their Open Road initiative in 2019. So 2 years later, we have a better one. And we also got some feedback from the Google team or from the domestic company. This is about logical synthesis, and it's also we won the champion in a row, 2 years, 23 and 24. And our undergraduate got the PhD offer from the UC Berkeley, who was the organizer and the host of this competition. And this is about quantum. We also can apply this idea for quantum circuits to automatically design the circuits of the quantum for different kinds of problems, like like in quantum chemistry. There are 2 ICML papers in these areas, and this is about the molecular property prediction. So this is a 3D molecule. It's a small column, right? A small molecule, and we develop a quantum encoding approach, and you can see that we can only use maybe just 1% of the parameters, but we can have the similar accuracy in terms of prediction. So this paper was also published in ICML 23. And we also have some works about protein docking. Actually, this is also a combinatorial optimization problem, and we got some papers, both in Nature Communication and iClear. Okay, so this is all my part, and thank you for your attention. Thanks.
Okay, thanks for the great talk. Is there any question?
I have a short question about the MIP part. So initially you said the existing software uses a fixed strategy, but in your case, you choose adaptively the right strategy. So this is a reasonable idea, but of course there's a risk of making a mistake, right? Sometimes you may choose the wrong server, wrong solver. Then, like, have you ever analyzed that kind of risk?
The good thing is that we usually will not degenerate it. We usually can keep it, no harm. So in many cases, we improve it. And
I mean, that's understandable, but still, like, you need to spend some time to choose the right solver, but sometimes you choose the wrong one.
It
takes forever, right?
That's possible.
And
because machine learning can always have this generalization issues, right?
Yeah, and have you ever observed any like failure case?
We have, but it's not very, very big and common. It's not very common. As long as your training data is expressive enough, we can make it more efficient. Okay. So actually, this technique has been adopted by Chinese companies in their commercial solvers.
So my question is about the risk. So like 1 out of 100 trials, if you make some critical mistake, then that's a problem for
Yes, I think this is a problem for productization. So you need to think about this. Thank you.
Okay, thank you.
Okay. Maybe if you have more questions, we can communicate with Junchi during the coffee break. Let's welcome Junchi again.
Thanks.
Everyone, my name is Chao. I'm a research scientist from RIKEN AIP Chibin's team. In this presentation, I'm going to talk about tensor networks. The tensor networks has been recognized as a very powerful framework to deal with many challenging computational problems in many fields, in quantum machine learning, especially for quantum machine learning. The tensor networks got to be a standard tool for both the numerical simulation and the theoretical analysis. But on the other hand, if you have the experience of using tensor networks, you must suffer from its model selection problem. Like you don't know how to choose which tensor network model for a task, and you might be also confused about how to select those hyperparameters. In my study, I call this sort of model selection problem as TNSS. It means Tensor Network Structure Search. And in this presentation, I will show you how to solve the challenging TNSS problem automatically and efficiently using algorithms. Well, so first of all, I will give a brief introduction about the tensor network, and its graphical representation. In my study, I consider a tensor just as a multi-dimensional array of real numbers. So as a particular case, a tensor can be a scalar. We call it a tensor of order 0. A tensor can be also a vector or matrix. We call it a tensor of order 1 and the tensors of order 2. So you can see the tensor's order just means the number of directions. Because the vectors have only one direction, so we call it a tensor of order 1. And the matrices have two directions corresponding to the rows and columns, so we call it the tensor of order 2. And in my study, we named the direction of the tensor as the mode, and the dimension along these directions is called the mode dimension. Well, so after that, in my study, we use the graphical representation to visualize tensor and tensor networks. Here we borrow the idea from the graph theory. We use a node to represent a tensor, use the edge to represent the mode, and use the edge dimension to indicate the mode dimension. The edge label. So in this example, it just means a tensor of order 1 because there's one node, one edge. So this is actually represent a vector. This is a tensor of order 2. It just corresponds to a matrix. So following this idea, we can define and visualize a tensor of any order and any mode dimension as long as we just add or remove some edges from the node. And after that, we need to define an operation on tensors. In my study, I'm mainly interested in the tensor contraction. So what the tensor contraction is, the tensor contraction is just a tensor-tensor multiplication. It can be understood as just the extension of the classical matrix multiplication as we learn in linear algebra. So here, suppose we have two tensors. So the tensor contraction can be visualized using the graphical representation just by connecting the two edges together. So this graph just means the tensor contraction of the two tensors. Because in this example, the two tensors are just the two matrices. So this graph in this example just means the multiplication of two matrices A and B. And then next, let's see a more complex example. In this example, we have totally 4 tensors, and their contraction can be just visualized by the graph like this. And these two graphs, just two simple examples of tensor networks. And from these two examples, we can see what the tensor network is. Intuitively speaking, the tensor networks are just a kind of graphs which is used to model tensor contraction. Well, so far, the tensor networks have many successful applications in both the engineering and scientific fields. And the success of these applications using tensor networks let me think about the question, why the tensor networks are so powerful? I think if you are familiar with tensor networks, you are naturally agree with the first point. That is, the tensor networks are so powerful because it can represent an extremely high-dimensional Hilbert space efficiently. In other words, the tensor networks can solve the curse of dimensionality. But in this presentation, I'll also highlight the second point. That is, the tensor networks are so powerful because of the flexibility of their structure. We have known the tensor networks correspond just a kind of graph. So for the different graph structure, we can construct various tensor network models. So just following this idea, many different tensor network models were proposed, and most of the applications using tensor networks are based on these structures. But on the other hand, due to the structural flexibility, it naturally raises a question about model selection. That is, if you have a specific problem and you would like to use tensor networks, you will be much confused about which tensor network model you should use for your task and which is the optimal tensor network structure. And this question serves as the driving force behind the study in TNSS. Okay, so in this presentation, I try to answer this question from the following several steps. First, I will tell you how to formalize the TNSS problem as a discrete optimization. And then I will introduce a specific algorithm by which we try to solve the TNSS using the well-known large language model. And in the last part, if we still have time, I prepare several examples to show you how to use TNSS to solve problems in machine learning. So first, let's see the question, how to formalize the TNSS. In my study, I'm mainly interested in three types of structure-related parameters. They are named as TN ranks, vertex permutation, and TN topology. To understand them, let's see one example. Suppose we have a tensor of order 4. It means this is a It means that this is a tensor who have 4 modes named as x, y, z, and t, and then we'd like to represent it using a tensor network. So in this example, the TN ranks just correspond to the age labels, which can be understood as a natural extension of the matrix rank as we learn in linear algebra. But the main difference is for general TN ranks is typically high dimensional. And the second parameter we are interested in is called vertex permutation, which just corresponds to the vertex labels. Because when we try to use a tensor network to represent a tensor, we need to build a mapping from the 4 tensor modes onto the nodes of the graph. And such the mapping is not unique, and the different selection of this mapping would affect the expressive power of the tensor networks. And because the mapping is mathematically equivalent to the permutation of the vertex, so we name it vertex permutation. And the last parameter we are interested in is called TN topology. This just corresponds to the graph, which is used to model the tensor network. So the whole TNSS problem just refers to the process to looking for the optimal combination of these structure-related parameters to represent a high-dimensional complex system using tensor network. And in this slide, I'd like to show you that solving TNSS is very challenging. On the theoretical side, solving TNSS has been proven to be NP hard. Even though for the most trivial case, that is searching for the optimal matrix rank, it has been well known to be NP hard. But finding the optimal matrix rank is not so difficult in practice because we can use the exhaustive search to find the best solution. But for general TNSS, it suffers from the so-called combinatorial problem. It means that the number of the structure candidates would grow exponentially with increasing the scale of the graph. So this fact means that the popularly used exhaustive search makes no sense anymore. So that is why we need to develop a more efficient searching algorithm. And so to this end, in my study, we consider TNSS as a discrete optimization problem. The objective function is like this one. We model it as a linear combination of the model complexity and the model expressibility. And then we use a graph G and its age labeling function R to model those structure-related parameters. So for the whole problem, we optimize the graph G and the function R to minimize this objective function. So it means that we are looking for the optimal tensor network structure to achieve a good balance between the complexity and expressibility for tensor network in a task. And for following these frameworks, we have proposed many efficient algorithms in the past years, but we have known the TNSS is theoretically NP hard. So these algorithms are just heuristics. It means that it may be very efficient for some specific problem or specific data set, but there always exists some new problem or data set that these existing algorithms will not work so well. So in this situation, we need to find a new algorithm again. So this situation like me think about question, how to break free from the circle of find a new problem, designing new heuristics, and then we find new algorithm again, and design new algorithm again. This makes the research a kind of a loop with no ends. So this situation let me think about how to break free from such an endless circle of designing heuristics. And this is a very common and general question, not only for TNSS, but for many problems of designing heuristics. And in the second part, that is our recent work, we found that the emergence of the large language models may provide us a promising opportunity to jump out of such a research circle in designing heuristics. So in this work, we consider to use the large language models to solve the TNSS problem. But here, we do not use the large language model to find the optimal structure directly. Instead, we hope to use large language model to design new and efficient searching algorithms instead of human experts. Our main idea is to design the prompts to instruct the large language models to mimic the behavior of human experts in the process of designing heuristics. And to achieve this goal, our first step is we need to understand how the human experts to do the research. So we realized is in the research, the human experts typically play a kind of role as a system. Here we consider the existing studies as the input, and then we output new studies. And in this system, we typically follow some standard so-called research workflow, which is also called the scientific paradigm. And in this research flow, it includes different blocks which correspond to the different phases in your research, from like the information collection, select the promising research direction, to do innovation, and use the experiment to evaluate your idea. And then in this work, our main idea is just to consider the large language model as a kind of agent to replace the position of the human experts to realize this research workflow for finding the more efficient search algorithm. And for this idea, we propose our methods called TN-GPS. The TN means a tensor network, GP means GPT driven, and S means search algorithm discovery. And in this slide, we showed how we design the prompts. Here we consider maybe the simplest case, that is we consider the prompts as a kind of frame. So for frame, we have the prefix, main body, and suffix. And in the prefix of the prompt, we put the basic information about the TNSS task and give the brief description about the interface for the algorithms. And then we use the suffix to restrict the outputs from the large language models. And then in the different blocks of that research workflow, we design a different main body of the prompts. And here we follow the idea of in-context learning. First, I give the list of the existing algorithms and then use the natural languages to ask the large language model to give us the expected results. So next, let's see the experimental results. This is a demonstrative experiment. Here we try to use the TNSS to looking for the most compact tensor network to represent the natural images. Here we choose the natural images just for demonstration. You can consider it as any high order tensors like the weights of the learning model, high dimensional quantum states or quantum operator as you wish. And here we totally choose 14 images in which 4 images is used to guide the large language model to discover more efficient searching algorithms, and then use another 10 images for testing the performance. And this is the objective function we used in the experiment. We use a compression ratio to represent how complex of the tensor network is, and use the approximation error to indicate the expressibility of the tensor network. And this is the experimental results. Each figure corresponds to one test image. The y-axis means the value of the objective function. A smaller value means a better performance. And in the experiment, we totally evaluated 7 algorithms. The first 4 algorithms are the state-of-the-art handcrafted by the human experts. The last 3 algorithms from hole 1 to hole 3 are the 3 algorithms generated by the large language model. And you can see in the most of cases, the 3 new algorithms achieve the best performance. So in the last part, I prepared 2 examples. Let's see quickly how to use TNSS to solve problems in machine learning. The first application is for quantum machine learning or for general quantum algorithms. Here, I'd like to say that TNSS is used to solve the so-called quantum knowledge distillation. As we learn that in quantum machine learning or general quantum algorithm, our knowledge would be fully encoded by the so-called quantum circuits. But in practice, the circuits would be seriously noised. That is the main reason to block the practical use for the quantum algorithms. For example, this is a standard circuit for a 4 qubits inverse quantum Fourier transformation. It means that we expect the output of these circuits can provide us the frequency information about the input signal. But if we implement these circuits on some real-world quantum devices like IBM-Q, the real output would look like this, which is totally different from our expectation. This is because this circuit is too deep. Every gate would impose a noise, and the accumulation of the noise will totally destroy the information of the output for this system. So to solve this problem, the key point is we need to find some new quantum circuits which have the same function like this one, but using fewer number of gates and shallower architecture. And because the quantum circuits just mathematically is tensor networks. So you can see this problem is just equivalent to the TNSS. That is to looking for the most compact tensor network to represent an operator like this Fourier operator. And in this paper, they realized this idea. They successfully compressed this quantum circuits. They call this circuits as they do not call it the circuits compression. They call it circuits distillation. And they mentioned after the distillation, the noise can be significantly reduced. In the second potential application, let's come back from the quantum to the classical universe. Here, I'd like to say that TNSS is also a prominent framework method to improve the efficiency for the model adaptation. Now, in the existing model adaptation algorithms, the low-rank adaptation is recently very successful. It allows us to fine-tune a large-scale model just to use our laptops. But its key performance bottleneck is from its low-rank structure. So to solve this problem, a promising idea is to represent these fine-tunable weights using tensor networks rather than low-rank decomposition. So in following this idea, we can represent these high-dimensional waves just to use these small tensors and avoid the unnecessary low-rank assumption. And this paper realized this idea, and they shows that this idea can achieve a comparable performance like a LoRa, but just using a much fewer number of parameters. But here I'd like to highlight that the side effect of this idea is you need to deal with such a complex, complicated tensor network. So it naturally raises the question how to design this tensor network for this algorithm. And you have known the TNSS might be very promising to solve this problem. So in conclusion, I prepared several takeaway messages. The first message is the TNSS can be used to maximize the expressive power for tensor networks in their applications. And then in this presentation, I proposed TNGPS, which is a large language model-driven framework for automatically discovering new TNSS algorithms. And the last point is, I want to use this work to highlight one thing, that the large language model can be used not only just the TNSS problem, they provide us a promising direction to solve many more broad and more challenging tensor problems. This is the papers involved in this presentation, and I prepared additional interesting slides at the end of my presentation. Thank you so much.
Thanks a lot. Is there any question?
Hey, hello. Thank you for a great talk.
Thank you.
You mentioned that TNSS maximize the expressive power of tensor networks.
Yeah.
I'm wondering how to. Are there any metrics to measure the expressive power of tensor network? Do we have known the maximum of expressive power?
Oh, okay. So I think for your first question is to evaluate the expressive power of the tensor network. I think it depends on your interested the task, because if we use a tensor network to represent a tensor, maybe in this case, its expressive power can be just indicated by the approximation error, right? But if in your problem you want to use a tensor network to represent your learning model weights or something, maybe a good metric is just the value of the loss function. And for your second question about it, there's the maxi. I think there exists some trivial results, like maybe it's a maximization of the tensor network. If you do not care the number of parameters involved in the tensor network, it's just a tensor network just equivalent to a high-dimensional matrix. Okay. So you can consider that the main goal of tensor network is to represent a high-dimensional large-scale matrix just using a few number of parameters. If you do not care how many parameters you use, maybe the maximized expressive power just equivalent to the expressive power of the matrix. Yes, but this result is kind of trivial, maybe not informative.
I see you mentioned the maximum.
Maximize means that we restrict the number of parameters. We use maybe a given number of parameters, but try to maximize expressive power. And on this point, maybe I don't know. There are some theoretical results.
So you are trying to maximize the expressive power.
Okay.
So you mentioned that tensor network has great expressive power in high-dimensional input.
Yes.
So is there any comparison with other network structure such as CNN or
For the
transformer?
convolutional, okay, I think it's a good question.
Yeah,
Yes, maybe there's not so many studies to compare this. There's some study, yes, there exists some study. I know some works to claim that the expressed power of the deep neural networks maybe is better than the classical tensor networks.
Oh, so there isn't a direct comparison between them?
No, because they are belongs to different domain sometimes.
Oh, okay.
Because a tensor can represent both the data and the weight tensor, so this comparison will be unfair. The CNN is a model that can only be applied to data, right?
Okay. Maybe we can have a talk
Sure,
about
sure.
the network structure later.
Yeah.
Okay, thank you.
Thank you.
Yeah, thank you, Charlie, for a beautiful presentation and talk. So, can you go back to the slide of the using quantum-informed tensor adaptation for
The model
alternative
adaptation
for
part?
LoRa?
Yeah.
So, can you explain this one a little bit more?
You mean which part?
I mean,
This matrix you just correspond to the fine-tunable with this part. In the conventional LoRa, the width is represented by the low-rank decomposition. Because of the low rankness, we can use the few number parameters to fine-tune a large-scale model. But the problem is because of the low rankness, it would affect the performance. We can't choose the too small value of R, right? But in this paper, you can find this paper, I like it very much. They re-represent this width, which corresponds to U, use the tensor network. But here, they do not use the general tensor network, they use the so-called quantum-inspired tensor network because they represent the tensor network with as a quantum circuit, but it's just a mathematical quantum circuit. It means that this U is represented by the tensor contraction of these small tensors. Each block corresponds to one small tensor, and each tensor is very low dimensional. Like maybe this tensor just maybe 2 by 2, or this tensor just maybe 4 by 4, or 16 by 16A. This is a tensor.
Yes.
Okay. Yeah, and so following this idea, this whole is just represented by the contraction of these lower dimensional tensors, and the fine-tuning precisely just optimize the value of these small tensors instead of optimizing the whole width. And from this construction of the tensor network, you can find easily that they can use a very few number of tensors to construct the U, but the U is high rank. That is why this performance bottleneck from the LoRa. That means that the main advantage of this idea.
Yes, so we can use this as a plug-and-play module into networks like LLMs.
So sorry, could you repeat that?
I mean,
question?
can we use that U models as a plug-and-play into the LLMs or?
Yes, I think this is the main function for any model adaptation method. We can plug in any. Yes, we can fine-tune it and fine-tune the different tensor networks for the different downstream tasks, and we can plug in it into the pre-trained large language model for your different goal and for different downstream tasks. Yes, we can.
Yeah. Thank you very much.
Yeah, thank you.
I'm very glad to be here and share with you some of our recent studies on medical image segmentation. So this work is focused on the uncertainty-based semi-supervised learning. Firstly, I'd like to introduce some basic concepts. So I think many of you are familiar with medical image segmentation. Basically, we need to identify some tissues, organs, or abnormal regions like tumors from the images. So from the view of machine learning, we need to output a segmentation mask And it's actually a pixel-wise classification results to show the predicted label for each pixel. So it's kind of pixel-wise classification. But this task faces many challenges. So the first challenge is label scarcity. Because you know the labeling process for medical images is very label intensive and also expensive, also needs expert knowledge. And annotations have very poor quality. So you can see from this picture, so these different lines are from different doctors. So their annotations are very inconsistent. So usually we need to average their annotations to get the final annotation for this image. And also, there is artificial variations in manual segmentation. And the second concept is uncertainty. So yesterday, I think many talks have mentioned this concept, but here the definition for uncertainty is a little bit different from yesterday's talk. For example, yesterday, Dr. Niu mentioned that uncertainty means some kind of vague labels for the definitions or for the descriptions of the images. But here, uncertainty means two kinds of things in machine learning. So the first is epistemic uncertainty. It mainly arises from the ignorance of the model. If we don't have enough data to train the model, then the model parameters is undetermined. And the second uncertainty is called aleatoric uncertainty. So it's kind of random noise. So these two kinds of uncertainties correspond to the model ignorance and the irreducible noise in the data. So this kind of uncertainty is irreducible. It's from the data itself, especially in the medical domain. Sometimes the imaging process has some noise. Yeah. So this kind of uncertainties cannot be avoided. Okay, here is an example. So to better illustrate these two kinds of uncertainties, I use some natural images. So here are some street views. Well, this is the original images, and these are the segmentation results. And let's focus on these images. For this column is the aleatoric uncertainty. You can find that, so here are the heat maps. The blue regions are certain regions, while the yellow and the red regions are the regions with very high uncertainty. So you can find that the high uncertainty regions are the boundaries of these objects, and also the objects far from our camera. Well, for this column, this shows the uncertainty regions for epistemic uncertainty. Well, for example, for this image, the high uncertainty regions are here, right? The footpath regions. So that means maybe the model rarely see the samples with such kind of footpaths. So here is I call it epistemic uncertainty. So if we have enough data, we have a lot of training examples, maybe in these examples, they contain such kind of images, then we can reduce this EU. Okay, various methods have been proposed to incorporate uncertainty into the semi-supervised learning. Here are some representative methods. So a basic method is to use Monte Carlo dropout to estimate an epistemic uncertainty. So, because you know in semi-supervised learning, a basic goal is to fully exploit the potential of unlabeled data, right? So usually we want to use the pseudo labeling. For pseudo labeling, actually for some unlabeled data, the pseudo labels are not reliable. But for others, maybe the pseudo labels are reliable, so we can use them as the training data, right? So here we can estimate the uncertainty for those unlabeled data for the pseudo labels. If the unlabeled data has a very reliable pseudo labels, we can add them into the training set. So this is the basic idea of the uncertainty-aware semi-supervised learning. So here, the key problem is to estimate the epistemic uncertainty. We can use the Monte Carlo dropout. That means we can use the Monte Carlo dropout to get the multiple results through the forward path. Yeah. And we can estimate the entropy of the results. If the sample has a very high entropy, then the uncertainty score is very high. And this method uses the teacher and student architecture, and we can enforce a consistent regularization term between the teacher model and student model. That means we require the teacher model and student model to have the same prediction results to add consistency constraints into the loss function. So a lot of studies focus on the consensus-based supervised learning. So we can not only enforce consistency constraints between student model and teacher model, we can also develop multiple decoders or multiple tasks and enforce the consensus-based constraints into the loss function. For example, for this paper, it develops multiple decoders and it enforces consistency constraints among these decoders. And for this study, it focuses on two kinds of tasks and enforce the consistency constraints between these two different tasks. And also some studies focus on prototype-based semi-supervised learning. So a prototype means a representative sample or the representations for the features for one class, right? So here, for these studies, we focus not only on the decision space, but also on the feature space. But for all these studies, they still have some limitations. The first limitation is that the quantification or the metric for measuring the uncertainty is limited. So most of the studies use entropy-based metric. So it's computation intensive. And also the potential of unlabeled data has not been fully explored. So next I will introduce some of our works to address these limitations. The first work is called FastNet. So in this work, we consider both kinds of uncertainties, the EU and AU. Because we find that previous works mainly focus on only one kind of uncertainty, either EU or AU, and most of them focus on EU, the epistemic uncertainty. They have not well addressed the noise and blurry cases due to the ignorance of EU, and also require the large computation overhead introduced by multiple forward passes. So here is the framework of our proposed method. So we aim to develop a unified framework to integrate these two kinds of uncertainties in the learning process. You can find that this framework consists of mainly three components: the EU assessment and the EU guided training and AU guided training. Here, instead of using the Monte Carlo dropout to assess the EU, we use multiple decoders to estimate the uncertainty scores. And here, for this component, we perform an unsupervised learning. It's EU guided training, use pseudo labels and also the consistency regularization. And for this part, we perform an AU guided training. So this part is supervised learning. We use the label data to estimate the parameters for a Gaussian distribution to model the distribution of the logit space. Okay, let's talk about details of these components. So here is the EU guided training module. So here we use multiple classifiers. We use 4 decoders. with different loss functions like focal loss, entropy, the entropy, cross entropy loss, and the IOU loss and dice loss, because different loss functions focus on different feature levels of the samples. Some loss functions focus on the low-level features, and some loss functions focus on the shape, the high-level features of the samples. So using multiple decoders, we can estimate the uncertainty score. And here we also enforce an consistency constraint between the teacher model and the student model. So you can find that here we use the pseudo label. There is a loss from the using the pseudo label, and also there's a loss from the consistency constraints. And we add these two loss together to guide the training. Here are the equations for these two kinds of loss. So this is the output for the student model, and this is the output for the teacher's model. So this is the consistent loss. And also this is unsupervised loss. We can see that for this whole module, the loss consists of two parts. This part is the consistency loss, and this part is the loss from the pseudo labels. That means, firstly, we use the student model to predict the pseudo labels for the unlabeled data, and then during the training, we use the student model again to predict them and compute the loss. Okay, here is the AU-guided training component. So this is a supervised learning. The idea is that previously, many studies assume that the predicted probabilities for each pixel are independent with each other. That means that for a certain pixel, the predicted label for this pixel is independent with the neighboring pixels. But here, we want to model the correlation between pixels. So we use a multivariate normal distribution to model the probability of these pixels. And we use the labeled data to learn the parameters in this distribution. So that is the basic idea. Okay, then for this component, for this module, the loss function also consists of these two parts, the cross entropy loss and also the loss from this part. And here are some equations. So this is equation for the multivariate Gaussian distribution. And also we simplify the original log likelihood into this one. Here we also use some relaxation. Here we use adjacency inequality and get the upper bound for the original loss function, because the original one is very hard to optimize. So we simplify this one to this one. By minimize this one, we can get a minimizer for the original loss function. Okay, now let's see the performance of the proposed method. Here is the results for the left atrium data set. For the first two results, we can see that here is the VNet with 16 labeled data. Well, for the second row is the upper bound of the whole model. We use all the 80 labeled data. So that is maybe the upper bound of the model. So let's see our model. The performance of our model is very close to the fully supervised scenario. It's very close to this matrix. So for these two metrics, the higher the better. For these two metrics, the lower the better. So you can see that the scores is very close to this fully supervised model. And it outperforms all the previous models. And also we can see from this visualization result that our model achieves a smooth boundary for segmentation. Where for some previous models, the boundary, decision boundary is not that smooth. Maybe we model since we consider the correlation between the pixel-wise prediction. So the decision boundaries are kind of smooth Also, here is the table for the ablation study. We demonstrate that each component of the method contributes to the performance enhancement. Okay. Now let's move on to the second method, APCO. Well, in the first method, we find that for some cases, previously I introduced that we estimate the EU using multiple decoders, right? Here, for the EU assessment module, we use multiple decoders to estimate, to compute an entropy from the result of multiple decoders. But for some cases, we find that, well, maybe multiple decoders, they all output the wrong prediction. So that means they are consistent. They reach an agreement, but the agreement is wrong. Their predictions are all wrong. So to handle this case, we propose another method. It's the APCO. In this method, we not only consider the consistency in the decision space, but also for the feature space. So here comes the question, can we capture the embedding distribution by considering all voxels? Because our medical imaging is 3D. So we want to explore the potential of both the labeled and unlabeled data in the decision space and also in the feature space. We want to explore the knowledge of the entire database. So here we develop a novel uncertainty-informed prototype consistent learning framework called APCO. And we propose a new entropy measure and an attention-weighted strategy for fusion. So in previous studies, the prototype is constructed using the labeled data. But here, for this method, we construct the prototype for each class using both labeled and unlabeled data points. So that's the basic idea of this method. Here is the architecture of the whole model. So it's also a student-teacher architecture. We can find that, well, so here for the student model, we use loss from the supervised learning, and also from the teacher model. Here we use the teacher model to predict for the unlabeled images, and also we estimate the EU, the uncertainty scores, and then convert the uncertainty scores into a reliability map. And also here, HL and HU denotes the representation for the labeled data and unlabeled data respectively. And we want to fuse these two kinds of representations and to construct the prototypes for each class. So for labeled data, we just use the average pooling to get the average representation for the labeled data. Well, for unlabeled data, we use an attention pooling strategy to get an average prototype for the unlabeled data. And then we fuse these two kinds of representations to get the prototypes for all the classes. And here we also perform a consistency learning. So we compute the distance between the prototype and also the representations learned by the student model or by the teacher's model. Okay, let's see the details of this method. The labeled prototype of class C is computed from the masked average pooling. So this is actually an average of the representations for the labeled data. And for unlabeled data, here we use a masked attention pooling. So here you can find that, well, here is a different term from this equation. Phi. Phi is from the reliability map. So it's a score denotes the uncertainty extent of this sample. So using this attention pooling, we can get the prototype for the unlabeled data. And next step, we want to fuse these two kinds of prototypes. So using this equation. Yeah. the final prototype is computed by a weighted sum of these two kinds of prototypes. Okay, then we compute a distance. It's a feature to prototype distance. As I mentioned previously, here you can see that the distance is between the representation yielded by the student model or the teacher model, and this is the prototype computed previously. So here actually we use the distance to approximate the probability of each pixel belonging to a certain class. So here are the consistency losses. For labeled sample, here we use the cross entropy loss, and for unlabeled sample, here we add the reliability score here to get the loss. Because for a certain unlabeled data, if it's unreliable, so we get a very low weight for it. Right? Okay, here are some results for this method. We also perform experiments on these two data sets. One is left atrium and the other is pancreas. The proposed method, APCO, achieves the best performance against the baseline methods. And also, we can compare it with the fully supervised model. You can find that for this matrix, the APCO performs better. Okay, except for this one. For these three matrices, it's better than the fully supervised model. Well, for ASD, it's also very close to this score. And for pancreas dataset, for these two metrics, it's better than the fully supervised models. Here is another data set. It's a more difficult one. It's three-class classification problem, and it's an aortic dissection data set. Also, our model performs the best. And this is the visualization results. This picture shows the aortic dissection organs. So you can find that here the yellow ones are the true lumen, and the red ones are the false lumen. Well, our method can achieve a very smooth segmentation results and very close to the ground truth. Well, some baseline methods, they cannot get a smooth and continuous segmentation results. And we also examine the segmentation results for the labeled sample and unlabeled sample. And we can find that for these two kinds of data, they have very similar prediction results. They have very consistent predictions. And as the training process, as the training progresses, the model tends to focus more on the decision boundaries, causing the uncertainty regions to shrink gradually. Okay, the last work is UpSum. So you know the large models are very popular nowadays. So we want to make use of large models to enhance our model performance. So here we use the large model called SAM, the segment anything. And there are many adaptations of SAM in medical field. So here we use MedSAM. The basic idea here is to fine-tune the large model, the MedSAM, and to update it to predict the domain-specific data sets. Okay, I will skip the details. Here is the architecture of this model. It consists of two parts. The first part is the supervised domain adaptation. We use some label data to adapt the large model. And the second part is unsupervised stochastic alignment. So for this part, we want to use the predictions from the large model to guide the parameter determination for the Gaussian distribution. So previously, we used a supervised method to estimate the parameters in this multivariate Gaussian distribution, right? But the label data are very limited. So here, we want to use the output of the large model to guide the selection of the parameters in the Gaussian distribution. Okay, I will not go into the details of this model, but just the basic idea is to make use of the outputs of the large model here are the experimental results. So in this case, it's a very extreme case. We only use one label data. By using only one label data, our model can achieve a very high accuracy. It's over 30% enhancement over the previous methods. But interesting, we find that if we use more label data, like 4 label data, the performance of the large model decreases. It's not as good as the previous models. So we think that maybe using the label data, the large models were trained, it's not as good as domain-specific models. Okay, here are some visualization results. Also, using our method, we can get a smooth and consistent segmentation results. Here are the conclusions. So in FastNet, our contribution is to fuse 2 kinds of uncertainties. Previously, the studies are focused on only one of them. And then in APCO, we focus on both the decision space and also the feature space to achieve consistency constraints in these 2 spaces. And in the third model, we make use of large model to better estimate the parameters in our distribution. Okay, in the future, maybe we can consider more complex distributions because now the modeling of this logic space is relatively simple. Now we only use the multivariate Gaussian distribution. Maybe we can consider more complex distributions. And also we can construct multiple prototypes for one single class. Now for a class, we only construct one prototype, but we can consider to construct a set of prototypes for one single class. Also, maybe we can use a memory bank-like mechanism to learn the prototypes. Okay, that is the last slide. This is my group. Thank you for your attention.
Thank you so much. Beautiful presentation. We are a little over time. Are there any single question or comment? Sure. Oh.
Okay. So with in the future work, for example, in medical imaging, what is the real noise distribution you may consider, you may find, or previously we all assume that Gaussian distribution or uniform distribution, and do you believe that what kind of distribution, noise distribution in the medical imaging?
I think it depends because different medical image types correspond to different noise distributions. So it's really a difficult problem in our study, yes. Maybe currently we can only address this problem by using a very simple distribution. Yeah, thank you.
Thank you. Maybe if I can add one question. In medical science, there are many rare cases. So there are many diseases that have big distributions, but you can have some very rare cases, like, like a single image, 2 images. Is this a problem for image segmentation also, or you can also deal with this kind of very rare cases?
Yeah, the rare cases are very common in this scenario, I think. So currently, I think there's no very good way to solve that. Mm-hmm. Yeah, maybe in the future, we can work out some special strategies to handle these rare cases.
Right. Yeah. Thank you very much.
Thank you.
Okay, so thank you so much for organizing this nice workshop. Unfortunately, I couldn't be in Tokyo, but I hope my talk will still encourage some discussions. So please just reach out to me with email if you have any detailed questions after the talk. So I'm going to briefly introduce light reinforcement learning, since it's a little bit outside the scope of this workshop. Then I'm going to recap a previous paper we had, where we look at symmetries of data and achieve out-of-distribution generalization, because this introduces a lot of the terms we need in the main part of the talk, which is like image-based environment generalization, also like via symmetries. So as you know, like in reinforcement learning, the main focus is to study an environment, and in particular, to have an agent interact in the environment and with the environment. And the agent has certain means of observing the world. And this could be image-based, this could be a state vector, depending on his or their abilities. And then it has the option to act and choose among either a discrete action set or a continuous action set. And in return, it changes its position in the environment or even the entire environment state. And it receives a new observation of the environment and receives a reward. So to set the notation, like one distinguishes between online and offline reinforcement learning, online is what we basically just discussed a second ago. So the agent can actively explore the environment depending on its actions. And the methodology here is that it collects into its memory the current state, so the observation, the action it takes, and the reward and the next state upon the action it took in the previous state. And then it collects all of this in the memory, and then you optimize by maximizing the reward based on previous experience. For offline reinforcement learning, we basically look at the memory of other agents which were collected in the past. So this is relevant for a lot of tasks where exploration is either dangerous or expensive. For example, for self-driving cars, you would not want to have the agent explore the environment because there could be casualties and so on and so forth. So you would train from a previously collected data set. And again, the logic is the same. So you optimize the policy so the agent's choices by maximizing the reward in the memory. And here, crucially, is no environment interactions are allowed, right? So it cannot like improve by exploring the environment. So here are examples for online and offline tasks. But in particular, there is a so-called D4RL dataset, which has previously collected trajectories from agents. So like there's the ant maze. So maybe it's a little bit small, but you can see it. There's like a robotic ant, and you have not only to learn the locomotion of the ant, but also to guide it through the maze. And then you have the classical mutual robotic tasks. Here's just one of them, which is the walker. And at the bottom, you have like robotic tasks, like in the kitchen, and other several tasks where you have to control a robotic hand or a robot arm. So what is like in image-based reinforcement learning? What do we consider generalization? So here you can see like an example of like the so-called RIKEN benchmark by OpenAI, which has been widely studied, and we will study it in the second part of the talk. So you can see that there are different games where you have to accomplish different tasks. For here are 3 examples: the jumper, the star pilot, and the big fish environment. And during training, you see this. While during testing, you train on like 200 levels of the game which the agent hasn't seen. And this can change the background, this can change the color of certain and structure of certain parts of the environment. And this is a significant distribution shift, which kind of connects into a lot of the talks we've seen yesterday. And I would advertise that like reinforcement learning, for that reason, is a very good playground to study distribution shift and algorithms acting and generalizing to distribution shifts, because the distribution shift is very clear and it's not non-trivial and can be controlled. So that said, so generalization in reinforcement learning, we can put it into maybe 3 categories, which are slightly different depending on how much the distribution shifts. So what I refer to as out of distribution generalization is really like, it's one distribution and we just cannot observe the full distribution because the data is limited. And however, during employment of the agent, it has to go to parts of the environment it has not seen during training, but it's the same distribution, right? But just not part of this distribution has not been seen during training. And then we have varying environment generalization, which is really like, it's either you can see it as a different distribution when testing the agent, or you could view it as like the same distributions with different parameters. And then there's something like task generalization. So the agent has to generalize to completely different tasks it has not seen before, which is maybe the most general, and that can be reviewed as an entirely different distribution. However, I will only briefly mention it in my ongoing work. We only touch this topic slightly. So that brings me to the second part, a recap of a previous work we had in offline reinforcement learning to introduce several notions and set the stage for the rest of the talk. So here in this work, which we published already 2 years ago, we look at the offline dataset I just introduced to you previously. And so those are the tasks names, Trim, Antmes, Adroit, and Franca. And we average over all the tasks. So each environment has several data sets and several different tasks. So here we just present the average normalized rewards. And basically 100 is 100%, right? So it's normalized to what you think the maximum is you can possibly achieve in this environment. And CQL is the standard baseline. And we actually are still state-of-the-art 2 years later in offline RL for model-free algorithms with this paper. And we're actually better than many model-based approaches. So just like to advertise it a little bit, so you can check like the state-of-the-art algorithms at the papers with code homepage, if you want to compare it to other state-of-the-art algorithms. So now what do we do in this paper? So offline reinforcement uses a static training data set, so no further environment exploration is possible. So our goal is to learn a specific latent representation and then self-supervise to infer symmetries of the data set or of the dynamics of the agent and its possibilities to act in the environment. And then in that way, extend the data set to genuinely out of distribution data points and have the agent perform better. So what are symmetries? So in particular, like in the entirety of this talk, we will distinguish between global symmetries and local symmetries. So global here is an onion. You can see if you flip it horizontally, you will get the same image. But however, it also has like a local symmetry. So if you zoom in almost in any patch, you get a rough approximate shift symmetry, right? So you can shift this image a little like by a discrete value, and it will be a symmetry. So those are two entirely different symmetries in the same environment. So what we do exactly in this paper is like, if you look at trajectories of ordinary differential equations from some initial time to some final time, we self-supervised learn local symmetries, which are actually local Lie groups, and then we can extend the data set in that manner. So here's some quick like image. So you see on the bottom that our shift symmetry it's a little bit jumpy because we only apply it to local points in a data set. We don't apply it to entire trajectories, which are not available per definition in this setup. But you can, so it basically extends to close by trajectories. And also we can, for example, in self-supervised way, infer the like global translation symmetry for these different tasks. So this is the cat ball where we have to learn to balance the ball by moving left and right. Okay, so we have set the stage now, and let me come to the main part of the talk, which is like my previous work on image-based reinforcement learning. So we just presented this like the week before at ICML with my collaborator at DeepMind. And so there is a problem, or I'd say like a feature of vision transformers in general, which is not desirable. Namely that the self-attention mechanism is permutation invariant. And this is usually only broken with like one initial layer, the so-called positional embedding. This applies for time series as well as images, by the way. And you can see that like it's not a desirable property. So the objective for the agent here is to reach the goal and fight some enemies. But you can see if you divide the image into patches, like it becomes non-solvable. And even this is even true for if you have only like a slight permutation invariance. Like here we only permute like 6 patches or 3 different like bigger patches, and you see that the position of the enemy changes. and even the final goal on the bottom can't be reached. So this objective is not feasible. So one somehow has to break this symmetry in a more elaborate way. So this is basically the thumbnail. So the first row shows that this is not equal for the task, but there are some intrinsic symmetries for some environments, local and global. And for example, for this environment, it's actually rotation invariant. So the action does not change if I rotate the image by 90 degrees. And we achieve like self-supervised generalization by reducing this permutation invariance to lattice symmetry. So the lattice symmetries for every image, like an image is always pixel-based, so it's on a two-dimensional grid, as well as the patches on a two-dimensional grid. So and the lattice symmetries are flip symmetries and rotations by 90 degrees and shifts. Okay, so let me go briefly through the technical contribution. So we actually had to introduce 3 technical novelties to be able to achieve this goal. The first is we have to modify the self-attention mechanism, and we call this just like graph symmetric self-attention, so GSA. Then also we have to make an interplay between local and global symmetries to get invariance and equivariance of the entire transformer model. And we have to then additionally introduce another layer which breaks flip symmetries, so only rotation invariance is preserved. I will go into this in a minute, why this is important. So let me just like highlight here. So we focus in this paper on image-based, so two-dimensional data, but this can also be applied to one-dimensional data for time series. Then the symmetries become, for example, time reversal symmetry could be broken, or you could break shift symmetry with this method. And also for 3D data, so for three-dimensional robotics. So let me briefly introduce the difference between invariance and equivariance, because these terms might not be familiar. So if I have like on the left side invariance and equivariance, if I compare these equations, so what do I see? So a row of G just means it's a representation of a group element G acting on the states S. On the left side, we see that this means acting on the states S, the function is invariant, so it doesn't change the value, it's equal. However, on the right side, we see that there is a secondary representation of the group acting on the function. So acting with one representation of the group on the states will give you the function acted upon with a different representation of the same group element. So that's the definition of equivariance. So here's the first technical contribution, so graph symmetric attention. And what is novel to the standard attention mechanism is that these colored G's, so those are graph matrices. So in fact, they can be interpreted as such. And maybe the best way to illustrate that is to look at the images, because there's a nice intuitive interpretation of those. So here's an example of an image with 3 times 3 pixels, or a patch with 3 times 3 pixels, or an image with 3 times 3 patches, right? So at the center, so represented for each of these patches is a node. And the notation here is that same colors means it's a shared weight, right? So this first graph here, if I flip it horizontally, you see that it will transform to itself. So it's not that immediate, obviously, but if you use that as a row in a graph matrix as such, you will get horizontal flip symmetric preserved by the self-attention. Here, on a second image, you get horizontal and vertical flip symmetry. You can see, flip it horizontally, you get the same image, and vertically. In the last one, you not only get horizontal and vertical flip symmetry, but also rotation invariance by 90 degrees. So here's the crucial fact. So for a lot of tasks, like it might be protein folding, which is a completely different subject, but especially now for reinforcement learning, changing the meaning of left and right with flip symmetries is not desirable, because it changes the meaning of up and down and left and right, so the agent would not know what he needs to do. So we need to introduce another layer, which breaks the flip symmetry but preserves rotation invariance, right? And that is done actually by summing over directed triangle subgraphs of the entire graph. And intuitively, you can also see that what happens here is if you actually flip this horizontally, you go from like something which moves in the right direction, something which moves in the left direction, also left way around the right-hand side. And however, if you rotate it, it preserves the orientation. So this actually then breaks flip symmetry but preserves rotation symmetry. So here is the transformer model. So we use, that's the second technical contribution. So so we basically divide it into a local transformer and a global transformer. Each of them have the graph symmetric attention instead of the normal attention. And there's no position embedding, right? So the local one, we look at local neighborhoods around every patch. Like that is just a collection of all the local neighborhoods. And then we divide this into pixels. So here, like it's the blue squares are supposed to be pixels, just for illustration purposes. And then we apply a local attention with shared weights for each patch. And then we can either choose to get invariant information or equivariant information out of the local setting. And then we just use this information in normal sense. And the global part is the normal vision transformer setting. And there are several options. You can choose local and global invariants, and like with all possible combinations. So we actually restrict ourselves in empirical analysis not to look at all the variations, but we look at two main ones, which is we call it SIET, S-I-E-T. So for invariant equivariance, so we use invariance and equivariance locally and globally. And the SIT has a rotation flip symmetry breaking layer as well. So it's invariant locally and globally. And what we find is that it actually like outperforms not only like vision transformers, which in general perform very poorly without hyperparameter search. So we use a backbone algorithm and do not change any hyperparameters. So it was optimized by the previous authors for ResNets. And we also tested on other equivariant ResNets. And we find a significant improvement. And the idea here is, so why does like using graph symmetric attention perform better than normal? The baseline vision transformer is that, like in a lot of tasks, it's actually not a sample efficient. So we just test this on a supervised Cypher 10 here, and we can clearly see the improvement of using our approach in terms of sample efficiency. So we also have to say we have some other results. This is not all the empirical results we have. We also tested in other, like, for example, the Atari 100K benchmark, which only uses 100 training steps in the Atari games. And I think we are the first to actually achieve, or to actually get vision transformers running on this sample efficiency benchmark. So one notable feature here is that the flip symmetry is broken in a self-supervised manner. So when we initialize the model, it actually is flip symmetric as well. However, in order to learn all of these tasks, it actually has to learn that flip symmetry is nothing so the agent has to learn to break flip symmetry, which basically means it has to tune these parameters in this triangles I showed you before to very large values. And it does that for all games. So, and additionally, we tested on simple task generalization. So this is the third category, which we only briefly touch. So in this simplified toy example of the mini-grid world, where the agent has to accomplish the tasks, in particular here, it has to cross the lava stream. If it falls into the lava, it dies, and it has to reach the goal. So the obvious thing is that if you rotate the image, that is actually symmetry for our network. So it's quite obvious that this will work very well for us. However, there's something more tricky, which is we can change just the goal position to different values and see if the agent actually has learned. So in the original task, the goal is always in the right lower corner, and it just has to learn to find the gap. And that's also what we do in training. And in testing, we just change the goal position and see how well it performs. And we see that we significantly outperform not only convolutional neural networks, but also vision transformers. So here's just a side remark. So this is just, I'm not going to go into that. That is just like a bug of the, it actually doesn't perform well here. It's just like naturally, it just learns to go down straight, which is in half the examples it works for this example. So it's just a side remark. So in general, the upshot is we work very well also for task generalization. So there's a second paper, which is currently under review, so the distribution shift can be generalized, right? So between training and testing, as we discussed before in these computer games. And here's the fact we have to balance what we call generalization versus sensitivity, right? So for certain tasks, we have to be sensitive. And for others, we have to generalize. And this trade-off is very tricky, and like very commonly in a state-of-the-art algorithms, this is achieved by just using data augmentation on the Q-learning algorithm. However, we impose we want to learn this in a self-supervised way. So we do not do any data augmentation. We add a layer, a preliminary layer, which we call color invariant layer, to the network, and learn this in a self-supervised way. Let me just now, since I'm running a little bit short on time, present the whole slide. So this is the theoretical background. So I'm going to be a little bit brief here. So S is the state space. So for a time series of input images, so those are the color channels. And then we actually use this symmetry properties of the singular value decomposition to show that this transformation. So this is now an example actually for only one time step. I'm not going to discuss the more time step case here. That if we add weights in this combination, then if the weights have certain properties, then we get that either this layer is invariant by any orthogonal transformation of the image, or a one-parameter family of special orthogonal transformations, or by a discrete set of 3 or 6 transformations. So it basically means by choosing the properties of the weights, we can have 3 categories of different symmetries we can preserve. So the first one is very general, so all orthogonal matrices. Then here we have SO3. And here we have a one-parameter family, which is a subset. And then we have 3 distinct categories, which the agent self-supervised will learn, it will identify. And since I'm running short on time, I'm just going to say on this slide that the preliminary layer, we do the same logic as before. We divide it into sub-batches and apply the singular value decomposition on the batches. But the weights are shared. So the weights of the previous equation here are shared among all batches. But you can have different weights for different features and choose different categories. And to test this, I need maybe 1 more minute. We introduce a new environment. So we modify the existing environment and introduce a river where the agent has to learn to swim across safely. And you can see that this is really color sensitive, because it basically means blue you live and orange you die. And additionally, we have a different category which we introduce, it can pick up either crops, so it can do some harvest, and get additional reward in not only going directly to the goal, but picking up some harvest first. And what we actually find is that, which was a little bit surprising, that we already find even improved training generalization for an algorithm which was optimized hyperparameter-wise for the neural network only. And then we can just say, okay, now let's generalize better on test time, and we see that we significantly improve not only the performance on the task itself, but also generalization over a wide range of image transformations. So we also test this on we find the same also more complicated tasks. So this is the computer game. So for the color sensitive environments, we find significant improvements of our algorithm, our approach. Okay, then let me stop here. I had 2 more slides about what I'm working on currently, but I'm going to stop here and take your questions. Thank you so much.
Thank you so much. Are there any questions or comments? Oops, silence. So maybe we'll let you present these 2 slides again.
Okay, good.
Sure.
So
go ahead.
Okay. So I think that's an open problem in the community, is that so there's actually another category of generalization, which I would refer to as hyperparameter generalization of the algorithm. And here the problem is that in contrast to even not only supervised learning, but also unsupervised learning, the algorithms are very much hyperparameter dependent. So you can get very destructive features if you change the hyperparameters. The algorithm might not learn at all. Then also there's something like catastrophic forgetting. The agent forgets for certain hyperparameters during a training everything, has to start learning again. And also it's like seed dependent, means like depending on which like random variable I start in how I explore the environment, it will learn completely different. And so here just to say that the approach is very going back to principles. So supervised learning does not have these shortcomings. So my ongoing work on or towards this solution is find simple guiding principles or assumptions we can employ the Q-learning to get rid of like some of these significant problems, which also limit like the applicability of Q-learning to more important tasks. So, for example, finance or autonomous driving, like, right? So that the algorithms are not that reliable. And we want to reduce the Q-learning algorithm to like the simplest working versions, basically, in this ongoing work. Okay, yeah, thank you again.
Great, thank you. Any other comments or questions? Or could you display your email so maybe people can send you email later?
Okay, sure. Let me just.
Great, so thank you so much for both the speakers. We have now lunch break until 1:30. So once again, thank you for both speakers.
Thank you.